27 I think are there. Let us start today's session. Before we go to the today's session, I'll just give some brief introduction about the previous what we did. So we are just comparing the size of reactors of MFR and PFR for any order, nth order reactions we are doing, and for a first and second order. As the order changes, how the comparison in the sense I'm talking only about the volume, either volume or space time, right? So tau by ca naught or v by fa naught, right? Fa naught and ca naught we know. So comparison in the sense always we talk about either volume or space time, right? So volume is more, your space time is more. Volume is less, your space time will be less. But for a design point of view, we try to reduce the volume because reduce the volume is having a lot of advantages of less space it occupies, less capital cost it will require, right? So less manpower also is required to operate. So a lot of advantages are there when the size of the reactor is less. As the size of the reactor is more, you have to spend more money for the same conversions or something like that. So whenever we are talking about reaction engineerings, we always talk about the volume of the reactor to be reduced, right? So before I start this session, I just like to inform you that yesterday one great professor from chemical engineering, uh, Dr. Stuart Fogler, he was passed away. He is the champion in of this chemical reaction engineering. So he wrote Elements of Chemical Reaction Engineering, one book. It's a very famous book, especially IITs, NITs, or even foreign universities. They follow Fogler because he'll give you in such a way that you can do the problem with computers because he does CRE reaction engineering with computers. That is solving the differential equations in terms of writing the programs and all. Right. So great book, Fogler. We yesterday he was passed away. In our time, maybe in their time it is on 23rd, but we came to know yesterday. So let us pray for his soul to be rest in peace. So with that, I will just try to start today's session. Whatever with the CRE, what we are studying, it is based on two books. One is Octave Levenspiel, he's still alive, is a great book. And one more, the same greatest book is that Fogler, Stuart Fogler, also Elements of Chemical Reaction Engineering. These two books covers the entire reaction engineering design of reaction engineering, right? So with that aspect, we'll just try to start today's lecture. So yeah, we are discussing whenever we tell about this comparison in the sense either in terms of tau, that is space time, or in terms of the volume. So when we compare, we are using for a nth order reaction, and then you can put order 1 and 2 and then compare. As the order increases, the comparison, the variation in the comparison or the variation of the sizes will be large. That is what yesterday we are seeing. I just recap what we did. So we are taking a performance equation for a CSTR or MFR. Tau m is Ca naught Xa by minus Ra. This minus Ra, you are assuming it is nth order, and then you are substituting. Then you are substituting Ca as Ca naught into 1 minus Xa by 1 plus epsilon A Xa. This is for the expansion also taken into picture. If you are not taking the expansion into picture, then you get a Ca is equal to Ca naught into 1 minus Xa. So if you substitute this here, then you land with this kind of expression. And if you rearrange these expressions, you are getting into in terms of this. And if you substitute that we are bothered only about the liquid phase reaction, then this sigma A will go to 0. Then you'll land with a simple equation. Like that you can do for a performance equation for a plug flow. This is the performance equation for plug flow. Whenever we are writing tau p and tau for mixed reactor and a plug flow reactor, that suffix we put tau p. This tells that it is the space time of plug flow reactor, and tau m is the space time of the mixed reactor. So M indicates mixed and P indicates plug, right? So this is just to compare ourselves what tau we are mentioning, right? So RA, if you substitute and then simplify it, you are landing with tau P Ca naught n minus 1 is this. And if you substitute, if you want to find the ratios, then you have to divide this MFR by PFR or PFR by MFR. That's up to you. So he is dividing equations 1 by 2 and then equating this epsilon A is equal to 0. Then you get a simplified form of this particular equation. This equation is valid when n is not equal to 1. That is, the order is not equal to 1. When the order is equal to 1, this goes negative and all with 0. So you land into problem, right? So other than that, this equation, if you put n is equal to 1, if you solve the what do you call the integral, then you are landing with this particular thing in the right hand side. And if n is equal to 2, that is the order is 2, you have this particular thing in the RHS, whereas the LHS is same. Now, if you draw this on a graph, now you can see here 1 minus x here I'm putting on the x-axis, and y-axis I'm putting the ratio of either the tau or the volume, whatever you are comfortable with. Both is going to be same. So XA is very small. XA is almost 0 initially. Therefore, you are landing with one value, and has at a high XA values, you are landing this side. So at low XA values, if you see, the comparison is very small, but the comparison will be very large, or the what do you call, the size ratios will be very large as your conversion increases. You can see very big difference, right? So it's not only with the order, even with the expansion factor. A positive expansion factor will again tilt your what do you call ratios to the right side of this curve, and a negative value of it will shrink this side, right? So this curve is a great curve which talks about the ratios, the comparison of the volumes or the space time with the conversion, right? So this is the graphical representation. From this graphical representation, we can know this is the initial conversion and this is the final conversion you want. The area under the curve will give you the PFR area, the PFR volume, and the area of a rectangle will give you the tau or volume of the mixed reactor. From this, we can tell for all positive orders, definitely your mixed reactor will have more volume, requires more volume than the plug flow reactor for a particular conversion. Am I right? So it's not that always a plug flow reactor will give you less volume. Instead of one plug flow reactor, one big plug flow reactor, you can have a combination of reactors so that your volume still it will be reduced. That is what I tried to show in the previous one. So in that there will be different combinations like plug flow reactors in series, small plug flow reactors in series, small CSTRs in series, or one plug flow reactor and one CSTR in series. Either it is the same volume or different volume, or one CSTR and one PFR in series, or you can have different combinations. One big CSTR, one small CSTR, one small plug flow reactor in series, either 3 or 4 or 5, whatever. So what will happen is, if you are having a mixed what do you call reactors in series, your volume required will be much lesser. That is what I claimed in the earlier class. Now I'll show you graphically how it will be done. This is for the multiple reactors in series, that is PFRs. Equal size PFRs are there, V1, V2, V3 till Vn. And F naught is the flow rate of first reactor, and X naught is the conversion here. So F1, F2, Fi and Fn, n reactors are there. We will write a derivation for n reactors. And V1, V2, V3 till Vn is the volume of the reactor. Either it is same volume or a different volume. If it is the same volume, you get n into V, that is the total volume. If it is a different volume, you get V1 plus V2 plus V3 till Vn, right? So that is what here. The total volume is V1 plus V2 if the volumes of the reactors are different. So for a ith reactor, you are writing the performance equation Vi by F naught. F naught is same, it is not changing because it's a plug flow reactor. So V I by F naught is integral x I minus 1 to xi. Just 1 minute, I'll just drink water. Xi minus 1 to xi dxa by minus Ra. So if you substitute V by F naught, volume is nothing but this the entire volume. This volume is nothing but the sum of the entire volumes. That is what you're putting. Sigma is nothing but the sum, whereas pi, if I write, it is nothing but the product. Sigma I is equal to 1 to n Vi by F naught, where if you substitute I as 1 to n, then you are landing with V1, V2, V3 till Vn by F naught. That is equal to V1 by F naught. If you substitute 1 here, you are getting at x0 to x1 dxa by minus Ra. Like that, V2 by F naught is nothing but if you substitute I is 2, you get this. So this integral, if you want to do it, it is nothing but the upper limit is the lower limit, upper limit is the lower limit, and inside it is same. Therefore, if you do the integration is nothing but you can put one integral from lower limit to the upper limit and dxa by minus Ra. This is from the basic calculus which you studied in the previous maybe 12th or 11th, right? So this is the expression Vi by F naught is x0 to xn dxa by minus Ra. What does this mean is instead of having small reactors PFRs in series, you can have one big PFR which is having a volume of the sum of the individual reactors, and then you can get the same conversion. That is what this equation means. Like now we'll see if there are MFRs in series, again equal size of the reactor is same. Then how it will be? So like that again, inlet is C naught, X naught is the initial concentration, F naught is the molar flow rate, and V naught is the volumetric flow rate. V1 is the volume of this reactor, V2 is the volume of this reactor, but he is putting equal size, therefore V1 is equal to V2 is equal to Vi is equal to Vn. Where the volume is there, then the tau 1, tau 2, tau 3. If the volume is same, the taus are also will be same. So if you are assuming it is a equal volume, then tau 1 is equal to tau 2 is equal to tau I is equal to tau 1, right? So the outlet will have Cn. Cn is nothing but the concentration at the exit of the nth reactor, conversion at the exit of the nth reactor, and V is nothing but the volumetric flow rate. And if you're writing the material balance for ith reactor, so ith reactor, this reactor, again, tau by C naught. Here I'm not putting A because we are writing for a generalized expression. Generally, concentration will be given in terms of C or C naught. Ca or Ca naught, that is just I'm writing for a reaction, A gives some product like that. Any kind of reaction, generally we put C. We won't put that suffix A or B or something like that. So tau I by C naught is xi minus xi by minus 1 by minus Ra. This is the performance equation of the MFR. If you don't know this performance equation, then again you have to write the material balance around it and try to get this equation. that we already derived how to get the performance equation. Even for this reactor also, if you don't know this, you have to write this ith reactor, what you call material balance, what is input, what is output, what is accumulation, and what is reaction, and then put input is equal to output plus reaction, and then you will get this, right? So if you can remember, you remember. Otherwise, you have to write the material balance and then strike out and then did. That we already done in the previous classes. That is why I didn't do. Tau I by C naught is xi minus 1 by minus RAI. Let us consider n is 1, n is nothing but order, and epsilon is 0, that is liquid phase reactions. Then xi we can write whatever, yeah, xi we can write as 1 minus ci by c naught, and xi minus 1 you can put 1 minus ci minus 1 by c naught. So if you substitute this, 1 get cancels, and you are writing for a first order minus ra is nothing but k into ci power n. N is 1, therefore ci. There is no expansion for our simplification. We are not using say expansion, so you are left with this particular equation. From this we can write the concentration of the previous reactor by the concentration at this reactor, that is ci minus 1. Ci minus 1 is nothing but the concentration in the previous reactor divided by the concentration in the present reactor. Ith reactor is what you are considering. So ci minus 1 by ci is 1 plus k tau I. 1 plus k tau I. So I ranges from 1 to n. Based on this, you can get different values of C naught by C1, C1 by C2, C3 by C3, C2 by C3 is equal to 1 plus k tau 3, like that. So if you are having taus are all equal, then tau I is nothing but tau, right? Tau I is nothing but tau. That is what we are doing here. As a constant volume process, all the tau is nothing but T bar in equal size reactors. Then we can write C naught by Cn is 1 minus xan. C naught by Cn, we can split this particular equation like this in terms of this. If you want to write C1 naught by, then C naught by C1, C1 by C2, like this. If you go on doing, this is a multiplication. This is nothing but a product that you are putting pi. That is what you will put pi. So C1, C1 cancels, C2, C2 cancels, Cn minus 1, Cn minus 1 cancels, C naught to Cn you get, right? What is C naught by C1? C naught by C1 is nothing but C naught by C1 is nothing but 1 plus k tau 1. Like that, 1 plus k tau 2, 1 plus k tau 3. That is what? Since tau I is same, you get n power n, correct? Because n reactors, so it is square 3, 4, 5 till n you get, right? Because it is all same. So C naught by Cn is like this. If you rearrange this equation, we can write tau n in terms of tau n is nothing but tau I is for each reactor, whereas n reactors are there. So you have to multiply that to get you to give you the tau for the n reactors. So tau n into tau I is nothing but if you rearrange this equation in terms of tau I, you get n by k, that is 1 by k into C naught by Cn whole power 1 by n minus 1. Here don't confuse with this n and this n. This capital N is for the number of the reactors, whereas small n is for the order of a reaction, right? So this term you will get, and if you substitute n tends to infinite, that is n number of tanks are there, infinite number of tanks are there, then this equation reduces to the plug flow reactor. Again, the derivation is not that straightforward again here. Please try to do this derivation. When this tends to 0, n tends to infinite, then how you are going to get this equation? You have to put a limit. You know how you have to do that. When there is a 0 by 0 limit, then from the basic calculus, you have to do something to give you this. Again, this derivation is not that straightforward. So don't forget about the derivation, how we are getting from this to this. That is not much important for us. Anyhow, you will get it. But the thing is, this equation plays a very important role. This is nothing but a plug flow equation. That what does this mean is, an equal size reactors in series, if you are connecting a lot of mixed size reactors in series, that you can eliminate that n reactors, and you can put one big CSTR, big MFR, PFR, having the volume equal to the volume, sum of the volumes of this reactor. Again, I tell you, earlier itself I told MFR, PFR is always better than MFR. Am I right? Because you get more conversion. But here what he is telling is equal size MFRs in series will be equal to one PFR, which is having the volume equal to the sum of the volumes of individual MFRs. Right? It's a very important expression. But why does this happen? Why does this happen if you are considering different reactors in series, n reactors in series? How this will go to a plug flow reactor? That is what is the biggest thing, right? So that is what you need to visualize. Why n number of mixed reactors in series? The conversion will be same to that of a plug flow reactor, which is having a bigger volume. That is up to you to give the answer. This is the third question I'm putting. This is the third question I'm putting. Here I'm not having any much difficulty because this is understandable. Small reactors is removed, and one big PFR you can put. But here this is surprising result. You are having a MFRs in series, but the result is going to be a PFR of one reactor. How you can explain this? How you can explain this, or how you can visualize this? Okay, I can show you some graphs and then show you, but does it make sense? That is what is the important thing. That's the third question, which I am not answering, that I'm not giving the answers. It is up to you to think why it is true. That is how you visualize that, right? It is true. That is definitely correct. But how you can visualize, or how you can justify that statement, right? So you can see here, that is what, again, I'm drawing a curve. This is the comparison of performance of series of n equal size mixed flow reactors with a plug flow reactor for the first order. He is assuming it is order is 1 and is comparing n equal size reactors with one PFR. So you can see this curve on the 1 minus XA on the x-axis. 1 minus XA is nothing but CA by CA naught, because 1 minus CA by CA naught is XA, right? And on the y-axis, you are putting tau n by tau p, or tau n by tau n tends to infinite. So you are having the tau of mixed reactors. Tau n is nothing but different reactors in series to that of one plug flow reactor. Either you can put in terms of taus, or you can put in terms of volumes, right? So for a first order reaction, you can see this is the curves. This is n is 1, that is first tank. This is second tank, 2 tanks in series, 3 tanks in series, 4 tanks in series, 6 tanks, and the tank tends to infinite is this particular curve, right? So this is for the first order reaction. Again, here I am showing you K tau. K tau, why? Because why you are getting K tau? This is the K tau. K tau is nothing but here Damn-Kohler numbers for a first order reaction. So as you increase the Damn-Kohler number, you know that your conversion is going to increase. Earlier itself I told. So this K tau plays a very important role. So you're drawing K tau. K tau, this is for 50, and this is for 20, this is for 10. So as the K tau increases, you know that conversion is going to be increased, because if you are coming this side, the conversion is increasing, therefore the value will come down, right? So you can see K tau as 1 here, K tau as 2, K tau as 5, like this, all right? Those are very important curve, which tells the comparison with n equal sized MFRs with plug flow reactors, along with one particular parameter, that is the K tau for the first order reaction. This is for the second order reaction. If you substitute order as 2 and then you can put kCa power square and then do the differentiation or integral. Then again, you can see this is understandable. N is 1. There is only one tank, two tanks, three tanks, and the tank is going to be infinite here. For infinite, it will be the flat curve like this. So you can see as the k tau here for a second order, you get one more extra term, that is Ca naught. For a third order, you get Ca naught square. The rest of thing is k tau will remain. So you can see as the k Ca naught tau is increasing, your conversion is going to be increased. Conversion is going to be increased, right? So let us do this is yesterday we discussed till now. This till now whatever I discussed in the last class I discussed. Now we'll see some important thing. If there is not a equal size reactors, then how you can compare? Again, here one important thing is if there is unequal size reactors, the volumes are different. The volumes are different in the sense your taus are also different. The taus are all different means you get different reaction rate. Here minus Ra1, here minus Ra2, here minus Ra3. These three are different. RAs are different because you have some concentration, different concentration. Here you have different concentration, here you have different concentration here because different taus are there. So it's not that easy when there is unequal size reactors in series, especially CSTRs in series. This problem looks very simple when we are having same equal size reactors, but unequal size reactors is not that easy. We'll see that what is happening, how you can find out the rate in that. You need to find out the rate because minus Ra, you have to substitute here minus Ra1, here Ra2, Ra3. How we do that? That is the biggest thing. So here let us see the notations. This is the inlet, C naught is the concentration, V is the flow rate, F naught is the molar flow rate, V1 is the volume in this tank, tau 1 is the space time in this tank, and a big reactor is there, one small reactor, big reactor here. The volume is V2, space time is tau 2. For this, what will be the inlet? The outlet from this is the inlet. The outlet from this is C1, V, F1. The volumetric flow rate is same. You are not changing the volumetric flow rate, whereas the molar flow rate may change. Molar flow rate, depending on the reactions, it will change. That is why F0, F1, F2, whereas C1 is the concentration of this particular stream. And you can put F1. Once you know F0, then you know the concentrations. We can calculate what is F1, molar flow rate. F0 into C1 by C0, we can get F1, right? So the outlet of this is C2, V, F2. Again, F2 you can calculate based on C0. C0 is no, F0 is known. C2 concentration we can calculate C0. So if you put substitute this, we can get F2, right? The outlet from this is C3, V, F3. F3 is nothing but again F0 by C3 by C0. This somehow you remember how to calculate this Fs, right? Because this is just a straightforward what do you call substitution. Right? So now we have to, there are three reactors. Now you have to write the material balance around the first reactor, around the second reactor, around the third reactor. So first reactor, let us write the component A. Here we are assuming that A is giving you some product. The reactant is A. The component A in the first reactor we are writing. So tau 1 is nothing but T bar. T bar is, if you are writing for a what do you call liquid phase reaction, there is no expansion. When there is no expansion, your space time and your average resistance time, T bar or holding time or whatever it is going to be same. But if there is an expansion, that is the volume is increasing, then the space time and average resistance time may be different. That's I gave one example of popcorn. If the popcorn is not popping up, if it is remaining as a seed, so it will have one space time. But if the popcorn is popping up, that is increasing in volume, definitely there will be change in the space times, right? So that is what this, right? V1 by V. because tau is nothing but volume by volumetric flow rate. What is V1? We can calculate C. We know that V by what do you call V by F naught is C by minus RA or XA by minus RA. That is the performance equation for the CSTR. So we can write T bar as V by volume by volumetric flow rate. That is the V1 is the volume of the first tank. So C naught minus C1 by minus R1. Minus R1 you are putting because here the rate is different. Rate is different, small reactor. So we rearrange this equation to calculate minus 1 by tau 1. So we are just ultaing this and putting 1 by. Then you have to put this ulta, that is flip this. Numerator becomes denominator, denominator becomes numerator, minus R1 by C1 minus C naught, right? C1 minus C naught. So keep this in mind, minus tau 1. Like that you do a material balance for the second reactor and the third reactor. I'll just do that. So like that, if for ith reactor, since we wrote here tau 1, this the same holds for all the reactors. Therefore, we can generalize ith reactor minus 1 by Ti is minus Ri divided by divided by Ci minus 1, because you are getting for the first reactor minus pre-initial. So for the ith reactor, what will happen? Ith reactor minus the previous one. That is what we get. That is what, right? So now how to calculate this particular thing, right? So let us draw a curve. Let us draw a curve minus R versus reactant concentration. So minus R versus reactant concentration, you are doing some experiment and trying to find out the curve. Let the curve is this solid line. Let this curve is this solid line, right? Now, how to calculate finding the compositions at this particular thing? How to find out the composition? The compositions of the outlet stream, which is coming out from the reactions or the reactors. One second. Yeah, man. So we need to calculate what is the compositions coming out from this reactor, or from this reactor. How we do that? This is the graphical procedure for finding the compositions. If you are not having this graphical procedure, it is very difficult to find out the concentration. You have to put a probe and then do the or you have to do a titer value or whatever it is. But the simple thing, graphical, the reaction engineering is all about drawing the graph and then finding out the concentrations or the conversions or the volumes from the graph. How we do that? Now you see this minus Ra versus concentration. This is the reactant concentration on the x-axis, minus Ra on the y-axis. This is the rate curve. If you assume that there is a, you know the rate curve, then C naught is the initial concentration. We know what is C naught because initial concentration. What we do is, this is the expression, right? Minus tau 1 R by Ci minus C1. So what you are doing, 1 by, this is on the y-axis, y by x, right? Y by x. Y is rate, x is the conversion. So y by x is nothing but the slope. So if I draw a graph between R versus concentration, this will be y is equal to mx or mx plus c, because you are getting c naught also, because this is the same concentration. So you will have a slope with minus tau 1. That is just like that I'm doing. Now C naught I know. This is the intercept. So what I do is, this is the rate curve. This is the rate curve. With a slope of minus 1 by tau 1, with this particular thing, having a slope of minus 1 by tau 1, minus in the sense you get a negative slope, right? With that particular slope, I draw a straight line because we know that this is going to be a straight line. Y is equal to mx plus c. So we try to draw from C naught with a slope of minus tau 1 and then project it or extend it to cut this rate curve with a slope of minus 1 by tau 1. So now once this particular thing is gone, again try to project down. That particular thing will give you C1. This C1, which is not able to this C1, which is the outlet concentration from C1, you can calculate by using this. Now having the second, now you need to calculate the C2 concentration here. How to calculate that? Now the inlet of 2 is C1. Initially the inlet of 1 is C0. So you are calculating C1 concentration. Now once you know C1 is the inlet to the second one, how to calculate C2? Again, now 1 by tau 2. 1 by tau 2 in the sense minus R2 divided by C2 minus C1, right? Because I is 2. So having a slope of minus 1 by tau 2, you know this particular thing. With a slope of minus 1 by tau 2, you can see here, the slope is not same because if it is a equal size reactors, the slope may be same. But this is unequal size reactors, one small reactor, one big reactor. So you get a slope also different. With this slope of minus 1 by tau 2, from C1, you extend it to cut the rate curve at a P. Again, that you project it down, that a vertical line, that is nothing but C2. Again, if you want to calculate C3, again you do with minus 1 by tau 3 slope, with a slope, negative slope, because negative minus is there. So you can again cut it on the rate curve and again project it to calculate C3. This goes on n number of times as how many reactors you want to keep. Yeah. Anything you want to talk on this? This is how you have to find out the concentrations if there is unequal size reactors in series, especially MFRs. Yeah, any one want to comment on this, or shall I repeat the processes, or is it understandable? Yeah, someone please.
So can you repeat the first one, sir? How to find the C1?
C1, right? Okay, fine. Now in this curve, you can see C0 is the inlet to this reactor and C1 is the exit of this reactor, which is the inlet to the second reactor, and C2 is the exit of the reactor 2 and inlet to the third reactor. So when a lot of reactors are there in series, we know only C0. C1, it is just going in a pipe, understand? So you may not have the time to take out and then do a titrations to find out all that. So we can calculate C1 using a graphical procedure, C1, C2, that is intermediate concentrations we can calculate by using the curve. How to do that is what I'm just showing you. Write the material balance around a reactor. Any reactor, the material balance will come like this: minus 1 by tau 1 or tau I is minus Ri by Ci minus Ci minus 1. That is what here. This is the material balance around any reactor of small reactor or a big reactor. For a small reactor, you get a one different slope. For a big reactor, the slope only will be different. This is nothing but If I draw this on the y-axis, this is nothing but minus 1 by tau is y by x. You assume it is y by x. Y on the y-axis, x on the x-axis. Y by x is nothing but slope. Slope is nothing but 1 by tau y. Or tau, if you are assuming first reactor, tau 1. If you are assuming it is 2 reactors, second reactor, then tau 2, tau 3, tau 4, like that. So, but this intermediate concentration, we don't know how to calculate that. That is what you are showing here. We know C naught because initially, what is the initial concentration of the reactant we know. So that you point in this particular curve, you have that point in mind with a slope of minus tau 1, minus 1 by tau 1, negative slope. This is negative. So that with a negative slope, you cut this rate curve, because this rate curve, how you are getting this rate curve? From the experiment. You have to do an experiment for A gives product, and then for the rate, whatever rate you are getting, you have to draw this particular curve versus rate versus reactant concentration. As the concentration is increasing, your rate increases, or as the concentration is decreasing, your rate also will decrease, because minus RA is nothing but minus dCA by dt is nothing but K into CA or CA power N or whatever it is. You have to calculate that K and N, right? So you have to know that K and N, and based on that, you can calculate minus RA and minus RA versus reactant concentration. You can draw a curve. Let this is some arbitrary what do you call rate curve. So you know C naught. From the C naught with a slope of minus tau 1, you extend with that negative slope a straight line, because this is a straight line equation, not a curve equation, it's a straight line equation. Let this straight line go and cut or bisect this, it's not a bisect, it is only cut this curve at a point M. That M straight A projected down straight line, so that you get C1, because this is C1 minus C naught. So C1 minus C naught, right? This concentration difference, right? So for the second reactor, again, you are putting I is 2, then 1 by tau 2 is minus R2 divided by C2 minus C1. Where is C2 minus C1? This is C2 minus C1. How to calculate this C2? That is what I'm telling. From C1 with a slope of negative, because we don't know what is this. We know this, we know this, we know this. We don't know this. So to calculate it from this, cut using a slope of negative, you cut the curve with that slope minus 1 by tau 2, and then project it down. Straight line projected down, that it will be C2. Like that, this process will go on till how many reactors are there. This is the graphical procedure to find out the what do you call compositions inside the mixed reactors of unequal size. Yeah, any doubt? Shall I give some time for you so that you recollect what is happening? Yeah, some 2 minutes break I'll give. Yeah. If you are having any doubt, you can put the question. I'll give that answer now itself. Next, we go for a very important thing. Before going to that, I just want to have some time in this. Yeah, here onwards, I told you that Vitlacharya movies will happen now. So this becomes that, that becomes this. Now I am going to compare a small reactor with a big reactor, first small reactor and a big reactor, or a big reactor and a small reactor. So very, only with the graph I will explain. I am not taking any examples. With the graph, you can understand this CRE much better than doing a problem. That is why this graphs, they will call it as a Levenspiel plots. The Octave Levenspiel, he gave beautifully in his book, Chemical Reaction Engineering by Octave Levenspiel. Beautifully, he showed how the volume of the reactor is less or more for this particular combinations. That is why these plots are called as Levenspiel plots. Right? Yeah, I'll just come back in 1 minute. just you have a recap. So welcome back. So this is the procedure for calculating the intermediate concentrations of in unequal size CSTRs in series. But again, here one important thing is how you get this rate curve, right? It's not that easy. How to get it? By differential analysis or integral analysis, you have to calculate the K and power, that is N. And then once you know that, then you get this rate. It's not that easy again. experimental. You have to do experiment for a particular reaction. You don't know the order, then you have to go do a differential analysis. You know what is the differential. You have to go on drawing the slopes and then try to find out the order. Once you know the order, the k is nothing but the slope. With that k, then you can put minus RAS k into CA power n. Then you can do it. Okay. Let us do next topic, very important topic. Determining the best systems for a given conversion. So here I'm everything I'm showing in a graph only, right? I'm not doing any problem. Problems we'll do later, or once you have the theory in mind, then you can see the problems even in 11 spill or even this Gavani, right? So again, I won't have much time to do all this problem because drawing this graph is not that easy. Again, I'm telling you. So in the first cycle test, a lot of people didn't draw the graph. You need to take a graph paper and then draw. Then only you get that real fun, right? So this everything is based on the graph only. Now here you can see reactors. Everything I'll show with the graph only, right? So let us do this. Yeah, this, right? So I'm comparing two cases here. Case one is I need to have a conversion of X2. I'm having two reactors, one small CSTR and one big CSTR. Let the initial concentration or initial conversion to this first reactor is 0. C naught is the concentration and F naught is the molar flow rate. This small reactor, mixed reactor, is having a tau1 as space time and volume is V1. The conversion coming out from it, let it be C1, concentration and conversion is X1. Here we are bothered about only X1. I am not writing C1. With the X1 conversion, we are sending it to a big reactor, having a volume as tau2, V2, and the conversion is X2. This is one case. In the case number 2, we are just flipping this. Instead of sending the initial reactant to a small reactor, what I'm doing is I'm putting one big reactor first, the same reactor, this big reactor, so having the same volume. This reactor first I'm putting, and then one small reactor I'm putting to get the same conversion. Right. Now tell me, which is better? Which combination is better? Either small reactor first and big reactor later, or big reactor first and small reactor later. The conversion is going to be same. I want to have, let it be around 90% conversion here. Even in this case also, I want 90% conversion.
Big reactor.
Is it both going to be same? Is it both going to be same? I mean, tell the volume of the reactor. Is it going to be same?
No, sir.
How you can explain this? Definitely, it is not going to be the same, right? So instead of this one reactor, you can have one plug flow reactor and mixed reactors in series. The combination is different. That is one reactor, first reactor is like this, you can see here. Yeah, one small reactor, MFR, then CSTR, PFR, and then again one big MFR. This is different than first if you put a big reactor, then this and again small. Or if you put CSTR, what you call PFR first and again combination, entire thing will be different. Each one will have different volumes. I mean, the total volume will not be same for the same conversion. The volume will be definitely different. How we show, how we, even if I show a problem, you get the volume different, but you won't get the feel why the volume is less. Now I'll show you in the graph. That's why Levens will introduce this graphs to make visualization very clear, right? Now let us do this case and then this case, right? Let us do this case. Here, what is, please listen carefully, all of you, those people who is not listening also, please try to concentrate, right? This topic is very important. You won't understand much even from the books, right? So they give different books will give differently the justifications, but the justification is going to be same, but in a different views they will give. So please try to concentrate on what is happening here, right? Now here I'm taking this particular thing. I'll just try to put the curve here. Yeah. Sorry. Let us take break here, right? So for this particular thing, what is this? This is a mixer reactor. This is a mixer reactor. So if I draw -1 by RA versus conversion, you know what is this what do you call it? Performance equation, right? What is the performance equation for CSTR? V by FA naught is equal to tau by CA naught
XA by minus
is equal to XA by minus RA. So this is nothing but 1 by RA into XA, right? This LHS I can split as that is equal to -1 by RA into XA. Can I write like this? The same thing, right? So this on the x-axis, 1 by RA on the y-axis is nothing but y into x or x into y. That is nothing but the area of a rectangle. Area of rectangle, right? Rectangle, right? L. Rectangle. Now I am drawing -1 by RA on the y-axis, x on the x-axis. For this particular thing, I am going from a conversion of 0 to 1. Let this is 0, and this is 1, this is 2, and still goes on, right? So where I have to put how much volume is required, we know that if I am putting this, if I calculate the area of this particular rectangle, I will get tau by CA naught or V by FA naught. If I want to have a volume, since I know the flow rate, this is the flow rate, I can calculate volume, or since concentration is known, I can calculate what is the tau. Correct. That is what I'm doing. This is nothing but area of a rectangle. So I'll draw an area rectangle like this. Correct. Correct. This area will give me either tau by CA naught, tau 1 by CA naught, or V1 by F naught or FA naught. This A is removed, right? For you can write for any reaction. That is why this reaction A, when you are putting, it is only for A giving product or something like that. So if you take any books, this A will be removed, right? So tau by C naught or V by F1, F naught, right? Now what is this? This is again CSTR. This is again a CSTR having the volume which is equal to -1 by R2 into XA2, right? This is XA1, because if you do this, you get XA1, right? XA2. So from X1 to X2, again draw the rectangle. This area will be equal to your, the area of the volume of this rectangle. Now you want to have a conversion of X2. For this X2, for this combination, what will be the entire volume? Volume is nothing but the shaded part. Volume is nothing but the shaded part. I'll just remove this. card. Again, I'll project it. Yeah, volume is equal to the shaded part. That is this particular thing. This particular thing, the red mark, whatever I am putting. This is the entire volume which is required for the conversion of X2 in this particular string, the area under this particular thing, entire one. Correct? This also will come. Let us take the other way. Let us take one more combination, that is first a big CSTR and then one small CSTR. Again, one big CSTR, the conversion is X1. So till X1, this you from X1, you try to project onto the y-axis to cut this rate curve. This is the rate curve. How you get the rate curve? Again, you have to do that differential and integral analysis to find out the rate. Right? So this particular thing, this entire, what do you call, the rectangle volume or rectangle area is the area of a big or the volume of the big CSTR. Again, from X1 to X2, there is one small reactor. So X1 to X2. So this is X2. So project it down and then here it is going to cut. This is X1. Right? This is for the volume of second reactor. Again, this entire thing is nothing but the volume of the entire reactor series, right? In this, which is better? So this volume is more or this volume is more? Yeah, any idea how to do that? Which to find out which volume is more and which volume is less?
Second volume is more.
Second volume is more. How you can tell from this graphical representation?
It's nearly 2 rectangles for the second one. And for the first one, it's half square.
Can we do one more way? How to, because it depends on either the combination, it depends on the area. If whatever area is small, that is good, right? So how to find that? What we do is, this is X2, right? I'll just remove this thing. Let me remove so that I'll come again. Yeah, now it is removed, right? Now you see, how to do this is they call it as the maximization of the rectangles. If you are able to understand, you follow, otherwise you just leave it. How to do this? This it tells now you want a conversion of X2, right? Till X2, you put this particular curve. This is the one reactor, one volume, right? One volume, entire volume is this. Entire volume is this. Because both are mixed reactor, therefore you are getting a big rectangle. So you see the shaded part, this entire volume is nothing but the entire volume tau total is nothing but, or T or V total, let it be V total or tau, whatever it is. V of shaded plus V of unshaded. Unshaded. That is, shaded is this, unshaded is this. Correct? Now to have less volume, what should have? Shaded should be more or unshaded should be more? To have less volume.
Unshaded should be more.
Because shaded, if it is more, that means that this combinations. Unshaded is what we not having any thing into picture, right? Here and here. So if you want to have this particular thing should be very small. Shaded should be small, means unshaded should be very large. If you make unshaded large, then you can tell that the volume required will be much lesser, correct? Compared to that. How to do that? That is what you do by area of maximizing the triangle. Method of maximizing the, if you can maximize this rectangle, you can maximize this rectangle. If you maximize this rectangle, what will happen? The area of unshaded part will increase. When the area of unshaded part is going to increase, the total volume is same. Therefore, this will be coming down. Correct. But how to increase this particular fellow? That fellow will be increased depending on the point of this x1. If you are putting a point here, then you will have this particular thing here. If you are putting x1 here, that is here, where how much you are going to put, right? So you get this particular thing. So the maximizing the rectangle is nothing but trying to calculate what is x1. Because intermediate concentration, that is what it is done by this. So maximization of rectangles is construct a rectangle between x and y axis, touching the arbitrary curve at a point M. This is what this you need to maximize. This is the thing which you, if you maximize this, the other thing will be coming down. How you do this? You know that the area of this rectangle is x and y. How you can maximize this? If you want to maximize this, the what do you call differential should be 0. This area can be maximized when the difference is 0. Differential. You differentiate this curve, y into dx plus x into dy is 0. That is nothing but minus dy by dx is nothing but y by x. That means that you are having a curve, but that curve, you with a slope of minus y by x, you try to draw a tangent. Try to draw a tangent. That tangent touches this curve at a particular point. If you have that particular thing, then you can have the maximum of this rectangle. If the maximum of this rectangle is maximum, the area of this is maximum, the area of this will be less. That is what you can do. That is what we do by maximization of the rectangles, right? The other procedure is what he is trying to do is you try to calculate the slope. You try to calculate the slope, and then parallel to this line, slope line, you draw a tangent. Draw a diagonal. Draw a diagonal in such a way that from this, with this particular slope, it touches this particular x-axis. That is what you call it as, you put and project, and this is the area of a rectangle. That is what he claims, right? So you can see here, maximization of a rectangle. This is the slope with the same parallel slope. You know what is here. With this slope, you try to extend, cut this particular same point. You just project it down, up, and then calculate this. This will be parallel to this. Now you see, this is a diagonal. This is a diagonal. This, when this rectangle becomes a square, almost rectangle becomes a square, then you have this what do you call area maximum, or this particular thing. So with this particular thing, whatever is this, you try to find out your x1 in such a way that you are placing this x1 here, in this. You try to place this x1 in such a way that you are having this square more or this rectangle more. So you find out where it is that and try to project it down, find the conversion of this. Whatever reactor is giving that conversion, you project you put that reactor first. Either it is small reactor or big reactor. It's not that always small reactor is better or big reactor is better. Again, it depends on the rate curve. Now, if this is first order, you will have one combination. If it is having a second order, again, it will have some more combination. So it depends on the rate curve. It depends on the rate curve. Try to find out this X from by using this maximization triangle rule to calculate what is the X1. That is where you have this area of the rectangle, which is unshaded maximum, that particular point is x1. So try to find the combination where you are getting that x1, that much. So either if a big reactor is giving x1 that, then you put a big reactor first and then a small reactor. Or if you are having a small reactor which will giving you x1 first, then you put a small reactor and then a big reactor. This is what you will do when you are having some big and small size CSTRs in series. So it depends on the rate curve, what reactor should be put first. But generally, for order greater than 0, for orders greater than 0, you can, I'll show you that. Yeah, you can see this is the 11 spell book, which you can read whatever I just gave you. So this is the curve what I'm showing you. And KLMN it should be as large as possible. If KLNM is as large as possible, then what will happen? The unshaded shaded part will be less, right? So that is what he's giving you. So to maximize this, you are considering the maximization of the rectangle. That is what I'm just showing you. So here one important thing is this particular thing. This is a very important bit. People miss this. If n is greater than 1, what is n? The n is the order. I'll just read this. The optimum size ratio for a two mixed flow reactors in series is found in generally to be dependent on the kinetics of the reaction. What do you mean by kinetics? It is nothing but the K value and n value. So you cannot generalize this, but a special case for a first order reactions, when order is 1 and equal size reactors are better. Remember that for a first order reactions, equal size reactor is better. It will give you a very less volume. Again, how he is doing it, he did lot of experiments and then finding out and telling that for a first order reactions, if you are having a different combinations of the reactor, especially CSTR, your equal size reactors are better. Generally, for orders greater than 1, remember, for orders greater than 1 in the sense 1.1, 1.2 like that. For all orders greater than 1, the small reactor should be come first. If there is having a two combinations of one small reactor and a one big reactor, it is always better to keep your small reactor first and then the big reactor. For suppose, if the order is less than 1, you know that when order is 1, always don't put unequal size reactors, only put equal size reactors in series. If you know the order of a reaction 1, if you know the order and the order is 1, definitely don't plan to go for a different size reactors in series, especially CSTRs. But if the order is greater than 1, then you can have a different series of reactors. Again, the combination, best combination will be the small reactor which will come first and then the big reactor. Again, it is not the same case if the order is less than 1 in the sense it is 0.5, 0.6, 0.7, then the large reactor should come first. The large reactor should come first. This he will explain this particular concept, especially these three, in a problem, in the example of 6.3. It's not that different, what you call rate curve is going to be different, right? For a order 1, 2, 3, the rate curve is going to be different. Based on the rate curve, your choice of the reaction is also will be different. That is what I cannot show you that problems now. I'll try to show, but you try to see the example problems, do the problems, because this is just putting that equation of a mixed reactor and a PFR and then doing it. Try to do. If you are having doubt, then I'll solve it out. But I'll do some problems, but not as you expect. That many, all these cases I cannot do because it takes a lot of time. right? So this particular thing is a very important bit in lot of gate questions or even interviews. They will ask if there is n mix reactors in series, if the order is 1, what is the best combination? If the order is less than 1, what is the best combination? Out of the best combination, what you put the reactor first, what reactor will be put first, and what reactor will be put second. Now you got what reactor to be put first and what reactor to be put second. But a graphical way also you can find out. But how you explain this? That is what is the biggest one. How you can give the justification. For an order greater than 1, why a small reactor should come first? Okay, from the experiment or from the what do you call problems, you can find out. Definitely the volume first reactor will be should be smaller as the orders are greater than 1. But why? How can you justify that without the problem? Just by looking at the expressions, and if you know that the area is going to what you call the reactor is order of a reaction is greater than 1, how can you justify the small reactor should come first and the small big reactor, then the average or the combination of these two reactors of small reactor and a big reactor will have a volume lesser than a big reactor and a small reactor? How can you justify that statement? It is up to you to visualize and then try to find out. Okay. Right. I'll just go to one more thing now. Let us have a combination of like this. Let us have a, I will just go again back to this slide presentations. Yeah, this is what. For n is equal to 1, if the order is 1, equal size reactors are the best. If you are not having equal size reactors, then again, you have to make some conclusion that you put a small reactor first. For anything better, you put a small reactor first and then go to a big reactor. Yeah, the answer lies with the same of the previous question what I asked. Why the MFR will have more volume than PFR? The answers for that and this entire thing is going to be only one answer. Once you know that answer, then everything will be clear. That answer I'm not giving. I am not revealing still. I'll reveal, right? When the order is less than 1, large reactor should come first, right? That you keep remembering it. Now we'll go to the next topic, then come back for that particular what do you call justification, right? I'm holding that justification for some more time. I just don't want to reveal immediately. The moment I reveal, the rest of the thing you feel as if it is very easy. It's not that easy, right? Yeah, let us use this combination now. Different reactors of different sizes. Now you see one small reactor, one big, one PFR, and one CSTR, big CSTR in series. Now what is happening? Now first reactor is X1. So till X1 is the area of a rectangle. Then you are having a plug flow reactor. So a plug flow reactor is from X1 to X2. So this is X1 and this is X2. What is plug flow reactor volume? Is nothing but the area under the curve. So area under the curve. And what is the third reactor? Third reactor is nothing but a big reactor, which is going from X2 to X3. This is X2. This is X3. So area of a rectangle. Area of a rectangle. So what will be the combination? What will be the entire volume of the reactor, which is going from initial conversion to the X3? It is nothing but this rectangle. I'll just put that pointer. Yeah, this rectangle, this particular thing, area under the curve, and then this particular thing, the entire one. Am I right? So this entire is the area of volume or volume area. I'm always telling about area. That is nothing but the volume or space time. This entire volume or the area is the area required for this particular combination. So if you are having different reactors, it is always better to draw a curve and then try to find out the area of. Again, I tell you, this area of a rectangle is easy to calculate because you know the height, you know the width, then you multiply both. But the area under the curve is what is difficult, right? So what you try to do is from this to this, you find out the middle point, then draw a like this, and then make a rectangle. Try to find out the area of this rectangle. Then this will be equal to, because this is not there, this is added. So we assume that this is equal to this, and then make the entire thing, right? That is easier. Otherwise, what you have to do, you have to count the number of the squares, and then half squares will be there. That it should be what you call. You have to have some justification to find out how many squares are there, and then multiply or add that squares to find out the area under the curve. So different methods are there. That's up to you. What is better to you? So this particular thing is V1 by F naught. This particular thing, area under the curve, is 1 second. Area again. I'll go ahead. This area under the curve is V2 by F2, and third one is nothing but V3 by F naught. So first reactor, you are having a mixed reactor. V1 by F naught is X1 minus X naught by R1. The second reactor is a mixed plug flow reactor. So you need to put a plug flow design expression. V2 by F naught is integral X1 to X2 dx by minus R. And the third reactor again is mixed reactor. V3 by F3 is X3 minus X2 divided by minus R3. This is R2, right? This is R2, right? So this is how we have to find out the areas of the total area or total volume of a different reactors in a series. Let us go for parallel. If the reactors are converted in parallel, what you have to do? So you can see here, CSTRs in parallel is nothing but one CSTR, second CSTR, third CSTR. The flow rate is FA naught. So the flow rate should be split between how many reactors are there. The flow rate should be split among them equally. So the conversion is XA1, the conversion is XA2, XAN, N reactors in parallel. So XA1, XA2, XAN minus RA1, RA2, RAN, because these are the rates. VI is V divided by N. What is VI? VI is the volumetric flow rate or volume of each one, is the entire volume divided by how many reactors are there. Generally, when you are connecting reactors, CSTRs in parallel, you have the same type of reactors, volume, same volume. So V is V1 plus V2 plus V3 till Vn. So capital V is nothing but small, yeah, how many types or how many number of reactors into VI. VI is the volume of single reactor. So when you are having like that, what is that is this FA naught is the entire flow rate. That flow rate should be divided with n number of reactors to give you what is the flow rate of each reactor. That is what this. The flow rate of an individual reactor is nothing but the total flow rate by the number of the reactors in parallel. So this is the flow rate is less. Here the flow rate will be half if there is two reactors. FA naught by 2 and FA naught by 2 will come. If there is 3 reactors, FA naught by 3, FA naught by 3, FA naught by 3. So the flow rate should be equally distributed. This is what is an important thing, especially when you are having reactors in parallel. It's not that even in CSTR, even in MFR, PFR, when you are connected in parallel, it should be the flow rate should be halved or depending on the number of reactors. So that is what, again, the reactor volume is going to be the same. V by Fa naught is XA by minus Ra, where Fa naught is nothing but FAI, because your entire flow rate is not coming. Only for this 1/3 or 1/4 of the flow rate is coming. Based on this, your volume requirement also will be less, right? So we will see if reactors are in parallel. This is in series. If you are having reactors like this, if PFRs in parallel and series, now you see these two reactors are CST PFRs in parallel series. But if you compare this stream and this stream, there are three reactors overall, two in series, one is in parallel, right? So along with that, what you have to do, how much flow rate should be done here and how much flow rate should be done here. We know that the flow rate, there are two parallel streams, therefore the flow rate should be half here and half here. But here flow rate, again two reactors are there, therefore 2/3 of the flow rate should be, how many flow rates are there here? That many reactants should be 2/3 should be sent here and 1/3 should be sent here. That is how many reactors are there in parallel and how many reactors are there in series. You have to measure, and then accordingly, when you are distributing the flow rate, you have to send 2/3 here and 1/3 here, then only it will be correct. So parallel combination, always the flow rate will be distributed accordingly. That is what is giving you here. If it is two reactors are in series, so you can put two reactors in series, and along with these two reactors, there is one a big reactor which is in parallel to this particular thing, where the flow rate V1, V2, V3 is the volumes of the reactors. So what we need to do is this flow rate, whatever is the initial flow rate, it should have this flow rate plus this flow rate, this flow rate plus this flow rate. The flow rate should be same. The flow rate should be same. Therefore, here there are two reactors. Therefore, 2/3 should be sent to this and 1/3 should be sent to this. That you can see as a problem in this particular thing. The best combination. Here, one more important thing is this particular thing just I gave. This is a very important bit. You try to make a note in this. I'll just read out this. The best arrangement of a set of ideal reactors is for a reaction whose rate concentration curve rises monotonically. This monotonically will happen when n is greater than 0. That means like this. I cannot write here. The reactors should be connected in series. They should be ordered in such a way to keep the concentration of the reactant as high as possible if the rate concentration curve is concave. If the rate concentration curve is concave, when n is greater than 1, you get a concave curve. For that, the concentration of the reactant should be kept as high as possible and as low as possible if the curve is convex, when n is less than 1. Concave curve and convex curve. So for this particular 6.2 figure, so you know this is concave. Therefore, what should be the best combination? Your reactor should be as low as possible, your conversion. Therefore, the ordering should be plug, mixed, and large mixed. For n is greater than 1. If the n is less than 1, it should be reverse order. That is big mix, big reactor, small reactor, then only plug flow reactor. The entire answer lies with this. Till now, I hold that answer, right? The concentration of the reactant is as high as possible or as low as possible. That is the answer for why the CSTR and PFR. CSTR volume is much higher than the PFR, or PFR volume is much lesser than CSTR. Why? Because in concentration of what do you call, in MFR, what will happen is the concentration of the reactant will be as low as possible. Whereas in PFR, the concentration of the reactant will be as high as possible. If you want to have a very high reactor, that is, you can see, I'll just show you here. So you know that minus RA, you know that minus RA is K into Ca power N. So the rate is directly proportional to the concentration for a what do you call this plug flow reactor. There is no mixing, right? There is no lateral mixing. So there may be a radial mixing, but there is no lateral mixing. So what will happen? The concentration progressively drops in the during the length of the reactor. So in CSTR, you get a PFR, your concentration of Ca will be very high, as high as possible it will be. So if you are having high concentration is high, therefore the rate will be high. The rate is high, the conversion also will be high. Now what is happening in this particular mixed reactor? This is the, so as this is Ca naught, this is Ca, and this is also Ca. As you put higher concentration thing inside, it is uniformly mixed. So it is suddenly dropping the concentration to A. A is nothing but the concentration which is going out. So due to the mixing, here due to the mixing, what will happen is the concentration will be as low as possible. If the concentration is as low as possible, then what will happen? Ca is low, Ra is low, therefore conversion also will be low. So it depends on your rate curve. If the rate curve is going to be, that is what is just showing you there. If the rate curve is going to be, yeah, you can see here. If the rate curve is going to be concave, where n is greater than 1, then you have to keep your reactant concentration as high as possible. How you can keep the reactant concentration as high as possible? Reactant concentration should be high only in PFR. That is why for a concave curve, when n is greater than 1, you should always have a what do you call it? A PFR first and then only CSTR. But it's not the case for concave curve. If n is less than 1, you get a concave curve. For this particular thing, again, it will be the reverse is true. Reverse. That is, you should have a large mixed reactor first, or if you are having a combination of PFR and a mixed reactor, you keep mixed reactor first and then plug flow reactor later, right? This I will show you when I go for one more topic. Now this will be surprising to you, but it is true, right? So I'll show you one set of reactions. I'll just read this. The reactions where the concentration curve passes through the maximum. Yeah, this is all. This point is very important. This particular thing is illustrated in the end of the chapter, the problems. You have to do the problems to find out this particular thing. So somehow you try to write down in your notes this particular what do you call bit, right? This is the best arrangement for an ideal set of reactors, right? I'll show you here. I'll go back again to this. Here I am showing you in parallel, right? So parallel, 2/3 here, 2 reactors are there, 2/3 here, 1/3 here. It will be the best combination, right? You can see some problems here. Try to do these problems. It is all worked out in the Levenspill. Some are in Levenspill and some are in Gavani. I'll come back to these problems a bit later. Let us do one important thing of. Till now we are discussing about the normal reactors. But what will happen if there is an autocatalyzed reaction? Autocatalyzed reaction is different. Your concept of whatever you are having, this mixed reactor is PFR is better, and MFR is better. That combination is going to be wrong. I'll just show you that. Yeah. What will happen if there is an autocatalyzed reactions? You know what is autocatalyzed reaction, right? Autocatalyzed reaction, some of the product will act like a catalyst. Some of the product will act like a catalyst to give you A is giving you R. Again write that. So I just write here. A plus R is giving you R plus R. Initially, that is A is giving you R, but this R will act like a reactant to give you a reactant or the catalyst to give you more R. That is what is the autocatalyzed reactions. There are some of examples. You can see these are some of the examples of that autocatalyzed reactions. Reaction of permanganate with the oxalic acid, combustion of fuel gas occurring in an adiabatic manner with a feed consisting of cool reactants. A lot of hollow form reactions is autocatalyzed reaction. Binding of oxygen with hemoglobin, right? So these are some of the examples of autocatalyzed reactions. Now, autocatalyzed reactions, how we can have the best combination. This is what now you see. We know that autocatalyzed reactions is having like this. In the previous case also I showed you. There will be the rate curve will be decreased and then increased because initially A is consumed. Initially A is consumed and R is being formed. More R will be formed, more R will be consumed, right? So your rate curve will again increase. There will be a point where you will have your maximum. This is just like your what do you call A gives R gives yes, like a series reactions where the maximum combination of R, because A is giving you R is giving you S. So there will be a place where you have maximum R. So in that process, you have a curve like this. You can have a curve like this. When you're having a curve like this is the rate curve minus RA versus CA. So you are having first one mixed reactor and one plug flow reactor, one combination. The other combination can be one mixed reactor and one plug flow reactor, right? I think this is not shown properly here. Yeah, I'll just go back to this particular thing. What is he giving? Yeah, this topic I have to talk one more time. That is because this is the autocatalyzed reactions. You are having with some R, the rate will go down, increases and then goes down because more R is being formed and more R is being decomposed and more A is decomposed. So you have this particular thing curve. So if you are having 1 by RA, this is with RA versus C, and if you are drawing 1 by RA versus XA, you will have this kind of curve. There will be a point where you have the maximum rate because minus 1 by RA is minimum, then RA is the maximum. The progress of the reaction is this, right? So you need to find out this point and you need to operate at this particular point to give you the maximum rate, right? So that is what you will do. In that, what will happen is now you see. This is the rate curve, right? This is the rate curve. Please listen properly. This will be the last topic. I'll just take 10 more minutes and then leave you, right? Only 10 minutes. Now the time is 10:14. I'll leave you by 10:24. If you leave. Right? Yeah, please listen here. Now this is the Now, what is the best combination? Please listen carefully. Now, this is the curve, right? Now, if I want my final conversion is somewhere here, XAF, having this, no, not there. Yeah, okay. Now you want a combination here for your final conversion here. If you want a final conversion here, this is 0, this is XAF. What will happen to the volume of a PFR or MFR? A PFR, let you tell PFR. PFR volume is nothing but area under the curve, correct? Area under the curve. So this entire thing will be the area under the curve. So volume of PFR is this much, this entire thing. But if you use MFR for the same type of reaction, or it is auto-catalyzed, what will be the area of MFR? Area of MFR is this is XAF. You are putting up, and this is the area of a rectangle. This is the area of the rectangle. So this dotted part, shaded part is the rectangle, MFR. This part, entire part is for the plug flow. Now for this conversion, what reactor is better? Where the volume is more? Where the volume is more? Plug flow is having the more volume than the mixed flow. So if you want a conversion here, then always mixed reactor for this kind of conversion is better for auto-catalyzed reaction because the volume is less. If you use the volume, mixed reactor volume this much and plug flow reactor volume this much, or the conversion will be same. So earlier itself I told my best combination will be the volume less. So if I want a conversion here, generally I go for a mixed reactor rather than a plug flow reactor. Again, it is not the same true. For the same curve, I want to have a conversion here. I want to have a conversion here. Then what is better? If I want a conversion here, if I use a plug flow reactor, this will be my entire volume. Area under the curve. If I use a MFR, what will happen? This is the final conversion. So area of a rectangle is the CSTR. So the area of a rectangle, this area of a rectangle and the area under the curve. If you compare both, generally the area almost it will be equally good, equally same, because this extra volume and this extra volume almost similar. So for this particular conversion, for this kind of reaction, it is auto-catalyzed. Either a mixed reactor or a plug flow reactor is good. Both you can use for the same conversion. Volume almost is same. Now what will happen if I want, for the same rate, I want to have a bigger conversion, like this. If I want a conversion XAF, more conversion, if I use MFR, the area of a rectangle is this. Area of a rectangle is this, correct? And if I use plug flow reactor, area under the curve is the volume. But this kind of reactor for what you call conversion. Now what is better? Where the volume is more? Definitely the PFR volume is less, whereas in MFR the extra volume is this particular thing. So for this kind of conversion in this reaction, you have plug flow better than the mixed flow. So for the same reaction, based on your final conversion where you want, you can have different combination of the reactor. Either here mixed reactor is better, here both reactors are better, here only PFR is better. Is it the same? Here PFR is better. Can we have much better combination for this particular conversion? For this particular conversion, for this reaction, you know that PFR is better because area under the curve rather than the rectangle. But is it the best combination? Is it the best combination? So what I do is, instead of one PFR, I know that PFR is better. For this particular thing, instead of one PFR, what I do is, because I know the maximum rate, right? At this particular point, I draw a rectangle. I draw a rectangle. Then what will happen? Till this particular conversion, I'll keep one MFR, which is having the volume this, and then from this conversion to this, I use one PFR. So in that process, what will happen? Instead of one PFR, one MFR and one PFR will give you much lesser volume than one PFR. Understood? So for that, how to find out this maximum concentration? That is what is important. So till that particular conversion, if you have, you know that at this particular point, your MFR is better. So from this, you go for a PFR. Then what will happen? This extra volume will not come into picture. So that will be the best combination for this kind of autocatalyzed reactions. For a autocatalyzed reactions, till your rate, till your maximum rate, it is always better to have a mixed reactor and then a plug flow reactor. That combination will give you an ideal or less volume compared to that of any of the reactor, right? So with that, I stop here. Important thing is at low conversions, mixed reactor is always better for autocatalyzed reactions. This is at a low conversions, your mixed reactor is better, but at a higher conversions, your plug flow reactor is more efficient. At a particular reactor in between low and high, any reactor is better. This is for only autocatalyzed reactions that you keep in picture. It's not that for a normal reactions, always at a low conversions, mixed reactor is better. That is wrong. Understand? Okay. I'll stop here as I promised. 10:22 it is. I stop here. Yeah. I'd like to take some questions from you if you are interested. Yeah. I don't know. I gave too much of notes today. Does it make sense or not? I don't know. Yeah. Still one more topic is there which I need to cover. That is before I go to the problems. This is what I didn't cover. That I will cover in the next class. That is nothing but this. Yeah. For autocatalyzed reaction, this is better. That is what I'm just showing. This recycle reactor is one important thing which I didn't cover. That I'll cover in the next year. This is one more set of reactor, recycle reactor. That I didn't cover. That is the only topic I didn't cover. I'll cover in the next class before we do some problems, or we do some problems now in the next class. Maybe tomorrow. I think I'll take first hour because afternoon I'll be busy. So I requested a mass transfer sir also. I think I'll take the first hour or whenever is the mass transfer period, then my period will be taken by him. Okay. Yeah, I'll send a message to you when is that period. I'll just okay. Any doubt? You'll have n number of doubts. I know, but you don't want to give. Yeah, Guru, 61 people are there. You please take attendance and then send it to me. This is 2 period attendance. So I'll give 2 periods. Already 1 period I missed. So I may put that period, that attendance to that particular period. Yeah. Any doubt? Shall I stop the sharing? Stop recording?